Okay, hi. So let's do something new today. So I actually I was a bit tired today because of the internship and a few other things. So I thought of not doing the contest, and you can see that it's been over an hour already. But I basically read the problems, and I think I can solve till E. So let's do a new thing today. I'll just these are the problems that I've already read. Let's just try to do them like really fast without any explanations, and after that I'll be explaining how to do these. Okay, actually, I didn't read this one. I read from B. Okay, yeah, so I think B was simple. Did I get it? A second. Is everything on? Okay. Okay. Yeah, this one wasn't true. Mhm. Okay. In every problem this happened. Okay. Okay. Right. This is the tournament thing, I think. Okay. No test cases. Hmm. Okay. Greater than 3. Okay. Hmm. Anyway. Okay. Yeah. Potentially symmetry, I think. Hmm. 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 Swiggy, 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 Swiggy. Okay. Yeah. Mm, that was Swiggy. Okay, code transfer. Mm, okay. Okay. Interactive. Okay. 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 Mm, okay, we got the inputs, and now I think we need the binary lip. Okay. Mm, what- Okay. Oh, okay. Okay. Mm, in each problem, same thing. Some icon. Ah, I need to practice this thing with the fingers. Okay. Uh, okay, so if this is correct, then we're done. I haven't read F and I don't want to. Oh wow, okay, yes, yay. So how long was this? Okay, less than 30 minutes. But to be fair, I had read the problems earlier. Okay, let's do a quick editorial for everything. Okay, yeah, so the code for this one, my code for this one is actually a little bit convoluted. Like I just did whatever the fastest thing I could think of. But the idea is pretty simple. It's just that between 1 and 2, the maximum of 1 and 2 will win, and between 3 and 4, the maximum of 3 and 4 will win. So, like, let's say the maximum of 1 and 2 is x, and the maximum of 3 and 4 is y. So, x and y should be equal to the top two elements of these four. So, to do this, I basically found x and I found y, and then I found I made two sets of like xy and the biggest two elements, and then they should be equal, something like that. So they are easier ways. If you can try one of them. Okay. Then let's come to the second problem. In this, yeah. So in this, there's a very cool observation is that yeah. So we want GCD of AI and 2AJ to be greater than 1. So what happens is GCD of AI and 2AJ is greater than 1, definitely greater than 1, if AI is even, right? So if AI is even, 2AJ will also be even, so obviously the GCD will be greater than 1. So it definitely makes sense to put all the even elements to the left, and then all the odd elements to the right. And any such configuration would be suitable because these even elements will agree with everything always. So you can rearrange them among themselves and it doesn't matter because they always agree with everything on the right. Regarding the odd elements, definitely never makes sense to put one of them before an even element because, as I said, even element agrees with everything on the right. So obviously they have to be on the right, the odd elements. But how do we know whether any ordering of these odd elements is good or not, or if there are some bad orderings? So it turns out there are no bad orderings because if both elements are odd, then you can just ignore that these two exist. The idea is something like if you have 3 and 7, so if they are co-prime right now, even if you double one of them, so 3 and 14 will also be co-prime. So there's no point. It's just that if their GCD is like so you can just ignore this two. Like this doesn't change anything. So this thing we know that it is symmetrical with respect to INJs. Obviously, any sequence you take and no matter how much you shuffle it, so shuffle them, the solution remains the same. If you shuffle these, then also the solution remains the same. So yeah, so all you have to do is just put the even elements first and then the odd elements, and that's exactly what I've done. Let me show you my code. Okay, yeah. So all right. So first I take the input, then I put all the even elements, then I put all the odd elements, and then I just simply count the answer using an n square loop, which would work here because um, let's go with the problem. Yeah, so it would work here because n is just 2000. Obviously, n square would work here, and so that was that. Yeah, so C is actually pretty interesting. In this, what we have to do is I don't know how many clarifications were given for this problem. Let me see. Sorry, not the home, the dashboard. I think yes, all the like 4 or 5 clarifications. Yeah, so these are not really required. The idea is just that a string is unstable if it has only 0 and 1. So obviously we have to replace all the question marks with something because otherwise the string won't be unstable. What we have to do is we have to make a string beautiful by like a string has 0, 1 and question mark. So what we have to do is we have to make it beautiful by replacing all the question marks with either a 0 or a 1. and after that it should become unstable. So when it is unstable, if it has alternate zeros and ones, so like if it is 0 1 0 1 0 1 or 1 0 1 0 1 0, then it is unstable. So yeah, so that's what we want to do, and we want to find the contiguous substrings of the string that are beautiful. That means that can be made unstable. So what? So let's yeah, something like this: 0 1 0 1 question mark 0 question mark 1, something like this. And we want to know how many contiguous substrings like this have um, can be made unstable, right? So we can see that this can never be made unstable, and that's because if you like put one here and zero here, then these two zeros are adjacent, and if you put a zero here, if you put a one here, then these two ones are adjacent, and if you put a zero here, then also the same thing. And so yeah, so this cannot be made unstable. So to make this thing unstable, it is necessary that it is of the form 0 1 0 1 0 1 or 1 0 1 0 1 0. So what is the invariant in both of these? So the invariant in both of these is that either all the elements in the odd position are 0 and all the elements in the even position are 1, or the opposite. So either all the otherwise all the elements in the even position are 0 and the odd position are 1, something like this. So what I'm trying to say is in both these sequences, this thing is invariant. So let's say if I is the index, or let's say if index is the index, so index mod 2 XOR index mod 2 XOR the element, right? So this is the invariant. So this is same for everything, right? Because like if we change the index by 1, we also want to change the element by like we also want to flip the element if we flip the parity of the index. So yeah, so that's what we want. Like and this has to be the same, right? So basically it means that either the element has to be same as the parity or it has to be different as the parity, right? So this thing is like an invariant, and we can call it the this is our invariant, and as long as this invariant exists, we can have the substrings, right? So what we want to do is we want to know how many substrings are there that end at this point and are beautiful, right? So this will be like a continuous interval. Like if this is beautiful, then all of these will also be beautiful, right? So we just want to know the minimum index such that all the strings in this range are beautiful. So when it will stop being beautiful, it will stop being beautiful when this invariant causes some conflict. For example, here if you find the invariant and here if you find the invariant, it will be different. So yeah, so we can just ignore the question marks for this, because obviously we can fill anything there and we can get the value of the invariant to be anything. But whenever we have a 0 or 1 already somewhere, so then what we have to do is we have to find the value of this invariant, and it can either be 0 and or 1. So what we want to do is we want to store the minimum the maximum index where we found the 0, and the maximum index where we found the 1. And like the one that is lesser of these, we have to leave that element out, right? So it is something like, let's say if we have the, like I'm just writing the values of invariants. Okay, so let's say if at one point the invariant is like 0, and at another point the invariant is 1. So obviously we cannot have both of these in a single substring, because it won't be beautiful. As I said, the invariant is same in the entire substring. So we don't want this to happen. So what we will do is we will keep the maximum index of the 0 and also the maximum index of the 1, and then we will find whichever is lesser of these. For example, if we had the 0 1 like this, then we have to exclude this and this entire thing. All of the strings present here will be included in the answer. Yeah, so that's what I have done in this problem. You can see. So in this array, I'm just storing the two invariants, the 0 and the 1, and initially both of them are -1. That means I don't have them anywhere. Then I run a loop, and whenever I find a 0 or 1, so this basically means that when I find a question mark, I don't do anything. So whenever I find a 0 or 1, I just calculate the value of invariant and store the maximum index where it is found. And yeah, so answer is just this thing. Okay, now just this one. Yeah, so this one I won't explain in much detail, but what I just did is this tournament structure that they have. let's just say I have this entire this same structure like this. So if I have the structure like this, then you can see that it is like a binary tree. So I just took that tree, and so yeah, so at each of these points I have some value, like I can have a 0 or a 1 or a 0 or 1 or question mark or 0, something like this. So I have some character at each of these positions. I said that here the answer is always 1. So obviously when there's no match, obviously at this point only one candidate has reached. That means they are basically asking us how many possible winners are there, right? So here the answer is always 1. And then whenever you have a 1 here, then you will just copy this value here, because whoever can win here can win here. And whenever you have a 0, you copy this value here, and for 1 you copy this, for 0 you copy this, right? And whenever you have a question mark, it means that this can win or even this can win, so both of them can win. So what you do is whatever value you have here, like for example here I have 1, here I have 1, so here you just add both of them and put a 2 here, then again here also you put a 2 here, then here you have a 0, so you'll just copy this value and 2 will be the answer. So something like this you had to do. And to actually do it, what I did was I used some tricks, kind of reverse the string, and like chose an indexing in which is like very suitable to me. So I basically, like, it is a bit complicated to explain, but I'll just try to explain a little. So let's say if I had a string like this, 1, 2, 3, 4, these are the indices. So what I did was I kind of reversed this like this, and it became like 7. Sorry. First of all, I added a blank character. So let's say I have a blank character here. Then I have 7, 6, 5, 4, 3, 2, 1. So these are now the new indices, and I'll just write the new indices here: 1, 2, 3, 4, 5, 6, 7, like this. And now the cool thing is that to get the children of anything, let's say if I want the children of 6, to get the children of this 2, I can just double it, and double plus 1. So these two are the children of this. So yeah, I won't explain it much. This is like I think whenever you store a binary tree in an array, that kind of thing happens. And yeah, so in that way I did, and I didn't have to actually make the tree, and it became much easier. But you can actually make a tree, like use an adjacency list, add everything to that, and do all that. That will also work. But yeah, so this is like a cool shortcut kind of trick, but little tricky also. Like I had to think a lot here, like how to actually get the right indexing and everything. But yeah, that's that. This one is actually very easy. The E problem. So in this, first of all, we have to notice that CI is greater than CPI. So that means that the children are always costlier than the parent, right? And what we have to do is we have to buy something from a path. So if we have to buy something from the path and the parents are cheaper, so obviously we will start buying from the parents. So we have a tree like this. It keeps on increasing, by the way. So like you can add more nodes to the tree as time passes, and everything is online, so you don't know the tree beforehand. But yeah, so something like, let's say if you start from here, then you want to buy something on this path, and you want to spend the minimum money, and you know that the cost here will be less than here, and will be the cost here will be less than here, and so on. So obviously you will start buying from here. If there is any gold here, you will buy from here, then here, then here, then here, and so on. Yeah, so that's what we want to do. And yeah, so this is not very bad, because let's say if we start from here, and we completely buy this thing, then only we will come here. Then if we completely buy this thing, then only we will come here, right? So whenever we completely buy a vertex, what happens is we have to do the same thing again. We have to again find a vertex and so on. So the thing is, we don't do this operation a lot of times, because whenever we completely buy a vertex, it kind of it's um, essentially removed. Like we will never buy anything from here again. So how many vertices are there? So there cannot be more than q vertices. So obviously, like this operation of buying a vertex entirely, we will never do it more than q times. So at max q times. Yeah, so that's what we will do. And now just the thing that is there is we have to quickly find which vertex is there that is unbought. For example, here you can see that if we start from this vertex, if we start from here, then we come here, then we come here. So we wasted a lot of operations. And what can happen is many times I can ask you to query at this point, and then you will have to waste these operations again and again, and then that will give you a TLE. So we don't want that. We want to quickly find the highest ancestor of this that is still unbought. So for this, we use a thing that is called binary lifting. That is kind of standard. So in binary lifting, what we do is for each vertex, we store the parent of parent, then the ancestor that is 4 level upward, 8 level, 16 level, and so on. So like this, we have something like that. And then what we try to do is we basically do something like a binary search to find the highest ancestor that still has at least 1 ton of gold left. So something like if we start from here, we will first see the 2 to power 18th parent, and we will see, oh, it is already bought. So let's leave it. Then we go to the 2 to the power 17th parent. It is also already bought. So let me go to the 2 to the power 16th parent. Then it has at least 1 ton gold. So we come here. Now from here we will go to the 2 to power 15th parent, then to the 14th parent, and so on. So in this way we find the highest ancestor that still has gold, and then we just buy stuff from there. So that's all we have to do. Yeah, so I just used the LCA code, which is based on binary lifting, to take some reference about how to write binary lifting. I could have done it on my own, but I just wanted to, do it a little faster. That's why. So yeah, so first of all, initialize the binary lifting array for the root, and then whenever you get a new vertex, then again just initialize the binary lifting array for that one, so that you have the parents at each level. Now this is the main logic of the program. So in this, what we're doing is we're taking the vertex and the total weight that we have to buy. So while the weight is greater than 0, that means while we can buy more stuff. And what we want to do is we want to take a vertex z, that is just the vertex that was given to the input, and we want to choose the vertex that is from which we have to buy stuff. So that is the highest vertex that still has at least 1 ton gold. So yeah, so simply using binary lifting, that's what we're doing, as I explained right now. Start from the I think this is H is 18 or 19, I think. Yeah, so start from there, and then while J is greater or equal to 0, just keep on decreasing it. And if there's gold there, just go up there. So if you want to know more about it, you can read about binary lifting. And then when we find Z, it is really simple. Just see the quantity that you want to buy. So it is the minimum of W and whatever amount of gold is left at that vertex. And the total amount bought gets increased by that. The total money spent gets increased by quantity multiplied by the cost at that vertex. We decrease W, we decrease the amount of gold that was present in that vertex. And yeah, so if Z is if that is equal to vertex, then we break. So this is because of the thing that was given to us, that if we cannot buy enough gold, where was it? Yeah, so if there isn't enough gold in the path, then we buy all we can. So that just means that yeah. So if I think instead of this, I could have written here only that while a vertex is greater than 0. I think that also I could have written. So yeah, so that's just this is just the case when the W is greater than the total amount of gold that is present on the entire path. And yeah, so that just print B and S, and that's all for this contest. Let's see how many people did F. I didn't really read it. Yeah, 23. I'm not in the mood. So yeah, thank you for watching.